Hello all, let's talk in this short podcast about sample variability, sampling distributions, and sampling distribution of sample means. Now, one of the reasons that we take samples is that we cannot get to take and measure the whole population. Okay? But now, when we take samples and we find the sample mean x bar, right, which is obtained from that sample, do you expect that this value x bar to be exactly equal to the population mean? Do you expect that? Well, your answer would be no. Okay? The sample mean will not be exactly equal to the population mean except for a rare chance. Okay, but that would be actually close. We do expect that to be close to the population mean if the sample from which we got the x bar is a random sample. Let me draw here a normal distribution, bell-shaped curve. Okay, let me draw that. And this is the population, okay, where the mean would probably fall somewhere over here. Okay, so that's going to be the mean of the population. We don't really know that, but we know that the mean is right there in the middle. So we took the first sample right here, right? Let's say that we take a second sample. But the first sample, we said that it's not going to be equal, right? But we will be satisfied if that is close, right? So if that sample mean will be close somewhere over here, right? That'll be okay. That'll be okay by us. So that's the sample mean of the first sample. What about if we take another sample? We take a second sample. Where does that sample mean fall? Probably will fall somewhere over here, okay? Maybe we take another sample, and then that'll be somewhere close here, right? And then another sample, that'll be close somewhere over here. Then another one, and another, and another, and another. And all of these sample means, right, would be somewhere here. Maybe some would be as far as this one, right? But we do expect them to be close. Maybe some sample mean falls directly and is exactly the same as the mean. But since we don't know the mean, we don't really know that. Okay? So now what we see here is that we have a distribution of sample means, right? Sample mean for the first example, sample mean for the second example, and sample mean for the nth example, or the nth sample. So when we take all these samples and we find the means of all these samples and we put these means somewhere over here, we can create a new distribution. So the first distribution that we saw here was X distribution. Of the population, right? So now we're seeing a new distribution of these values, which are sample means. Okay? So this new distribution now will actually be tighter. If you see, that's how this distribution will be. And this is called the X bar, or X bar distribution. Okay? Okay. So what do we observe here? We observe three things. That if all possible random samples, each of size n, right, each of size n, are taken from any population, such as this X distribution here, with a mean of mu and standard deviation of sigma, right, then the sampling distribution of the sample means, this sampling distribution of the sample means, will have the following properties, okay? One will be that a mean of the sample means, the mean of the sample means will be equal to the population mean. Okay, so that's one. Two is that a standard deviation of the sample means, will be equal to the standard deviation of the population divided by the square root of n, because n was possible random samples with size n. N is the size of all possible random samples that we got. Okay, and three, which is very important, is that if the sample population or the X distribution, right, which is in red right here, is normal, okay, then the sampling distribution, this sampling distribution here, X bar distribution, will also be normal for all sample sizes. So this is called central limit theorem. So this theorem is really very interesting, okay, because the first and the second part here, first and the second part, tell us about the relationship between the population mean and standard deviation and the sampling distributions of the sample means. Okay, so there is a relationship there. So the mean of the X bar distribution will be equal to the mean of the population, okay, and the standard deviation of the X bar distribution will be equal to standard deviation of the population divided by square root of n, which is the sample size. Okay, now this standard deviation, I'm just going to write this here, standard deviation of the sampling distribution will be called standard error of the mean, to avoid confusion with the standard deviation of the population. Okay, standard error of the mean is the standard deviation of the X bar distribution, or standard deviation of the sampling distribution. Okay, so we need to know what these are, and the relationship, which is the standard error of the mean, will be equal to the standard deviation of the population divided by the square root of n, which is the sample size. Okay, but what about this third statement here? Okay, this indicates that the mean value of only a few observations, okay, will be normal when the population distribution is normal. When the population distribution is normal, only a few values will be normal, right? But what about the others, when the population distribution is not normal? When the population distribution is uniform, is skewed, or otherwise not normal, what happens? The central limit theorem actually tells us some very important information, okay? And that important information is that the sampling distribution of sample means will more closely resemble the normal distribution as the sample size increases. So the sample distribution is going to be normal when the population distribution is normal. But when the population distribution is not normal, then the sampling distribution will be normal as the sample size n increases, or is large enough. Now what is this? What does this mean, large enough? Usually it is accepted that a sample is large enough when n equals or is greater than 30. So a sample is large enough when that sample size is 30 or greater. Let's talk now about the application of the sampling distribution of the sample means. Okay. Now here's one thing that we need to know here. We do the application for real world problems again by using and finding the probability. Okay, and we are going to be able to answer probability questions with the aid or the help of the standard normal distribution, right? But when do we have a normal distribution of the sample means? We do have a normal distribution of the sample means when the population is normal, first of all, or when the population is not normal, but the sample size is large enough. Okay, so these are the two conditions. Either we have a normal population, in which case the distribution of the sample means is normal, or when the population is not normal, but we have a sample of larger than 30. In that case, we do get a approximately normal distribution of the sample means. Okay. So in order to answer questions about the probability, okay, with the help of the standard normal distribution, we need to know about the z-scores. Okay, z-scores, right? So now we need to convert x information into z-scores. So the computational formula, or the transformation formula from x to z, will be with the help of the z-score formula, which is going to be z equals x minus mu over standard deviation. So this is the formula that helps you find z in a normal distribution bell-shaped curve. Okay. Let's consider now a normal population with a mu or mean of 100 and a standard deviation of 20. Okay? Now if a random sample of size 16, so size equals 16, I'm going to write that with a different color, right, is selected, what is the probability that this sample, okay, that this sample will have a mean value between 90 and 100? So the mean value is x bar between 110 and 90. Okay, so what is the probability that we have this? What is the probability that the mean of the sample will be between 90 and 100? Okay, this population now is normally distributed because it was given in a normal population. We said normal population. Okay, so in a normal population, okay, the sampling distribution of x bar will be normal too. Okay, because normal population yields a normal x bar distribution or normal sample means distribution. Now we need to convert the statement of P of x bar smaller than 110 and larger than 90 to a probability statement involving the z-score right here. Okay, so the sampling distribution that will be shown right here, let me write and do this. So we have a mean of 100, okay, standard deviation is 20, so now we need to find out 110, somewhere over here, okay, and 90. So we need to find the probability of this particular area. But if you remember, this is the x bar distribution. This is not x. This is not the population distribution. This is the sample means distribution of size 16 right here. Okay, so what do we have here now? What do we have here? We need to transform the z formula here so that the z-score corresponds to a known value of x bar. Okay, so the z will be looking like this. Since the mean equals the mean of x bar, right? And remember this, standard deviation of the x bar or standard error of the mean is standard deviation over square root of n, then this formula here will be z equals x bar, right, x bar minus mu of x bar divided by standard error of the mean. So the z formula of a sample distribution is this: z equals x bar, this is x bar, minus the mean of the x bar distribution over standard error of the mean. This now will be transformed as follows: z equals x bar minus mu over standard deviation divided by square root of n. Why is that? Because according to the central limit theorem, right, mu of x bar, or the mean of sample means, will be equal to the mean, and the standard error of the mean will be equal to standard error divided by square root of n. So we just replaced these right over here. Okay, so now this is the z-score for the sample means distribution. Okay, let's solve our problem now. So the first step to solve this problem is to find z-scores for x equals 90 and x equals 110. So we're going to have to find two z-scores. 2 is find area or probability associated to these z-scores that we find in step 1. 3 is subtract smaller area from larger area. Okay? Smaller area from larger area. And that would be the probability. Okay? That would be the probability that this sample will have a mean value between 90 and 100, just like you see it here in this bell-shaped curve here. Okay, so let's start. The z-score for 90, okay, will be z-score for 90 will be x bar, which is 90, right, minus the mean, which is 100 here, divided by standard deviation, which is 20, divided by square root of 16. Okay, so that's going to be minus 10 over 5. Why is it 5? Because square root of 16 is 4, 20 divided by 4 is 5, so that is minus 2.00. Okay, so the z for x bar 90 will be minus 2.00, so it would be somewhere over here. Okay, actually the z-score is minus 2.00, so that's what I'm going to write right here. Now the z-score for 110, x bar equals 110, is 110 minus 100 over 20 divided by square root of 16, and that's going to be 10 over 5. That's going to be plus 2.00, so that the z-score on the right side will be 2.00. Let's find the area now. So the probability of x bar being between 110 and 90, okay, will be written as the probability of z between 2.00 and minus 2.00, right? Which will be written as the probability of z smaller than 2.00 minus the probability of z smaller than minus 2.00. Why? Because the probability of, to the left of the positive z of 2.00 is the largest area minus the smallest area here. So what is the area to the left of z of 2.00? That is 0.9773 minus the probability to the left here, okay, is 0.0228, and that's going to give us a probability of 0.9545, or written in percentages it's going to be 95.45%. So we answered the question with the probability that this sample will have a mean value between 90 and 110 is 95.45. Okay, so that's how you work with solving applications of real-world problems in the sampling distribution of the sample means.